Hi again. We're going to try to run through just the rest of the notes. And then after we run through the rest of the notes, you'll have a few different assignments over this chunk of notes, but I just wanted to kind of put it all together into one spot for you to watch. So if you need to watch part of it, stop and then come back to it later. That's totally fine. But the last part of the notes, I missed these yesterday when I recorded. We were talking about chemical versus physical changes. And when we were talking about chemical versus physical changes, you have chemical reactions, which is a different term for a chemical change. And a chemical reaction is when you're making new products. So you're going from one thing, changing it completely, and then turning it into something else. So when you're going through a chemical reaction, the something that you want to ask yourself is, does my before and my after look completely different from one another? The best example, probably the grossest example that I can come up with is eating something. So if I eat a bag of pretzels, the before and the after, I'm not going to get into more than that, looks completely different. Once you have your after product, you can't go back to that pretzel that you ate. So stay with me there, but something people always kind of resonate with. So chemical reactions, you're going to look at your before and your after, and they're going to look different from one another. If they do, it's a chemical reaction. Whereas if you have a piece of paper and you rip that piece of paper, it still looks like paper, it's just in a smaller shape. So if you're making new product, it is a chemical reaction. Now, ways of knowing if a chemical reaction happens or not. I just lost my, sorry, okay. Sorry, I lost my picture-in-picture. So ways of knowing a chemical reaction happens or not is to look at the substance, and when you look at that substance, if you have a change in color, so if you have a match and that match burns, you go from the wood color to black. That's a change in color, so that is a way that you know you have a chemical reaction. If it changes smell, again, if you burn a match, your ashes smell completely different than the wood that you started with. Creating light, match again. That creates that light, it's the gases that are burning. So that would be an example of a chemical reaction. Creating heat, again, we're going back to fire. You're creating heat, or sometimes it might feel colder. If you think about those little cold packs, when I taught kindergarten, we would send kids to the nurse, and they had those little disposable cold packs. They were like little rectangles, and you'd have to break something on the inside, and then they got real cold. The nurse would give those out for everything. So you got a little Bobo, and she gave you an ice pack and a Band-Aid, and everything was all good again. So that is actually a chemical reaction. We're going to make those second semester, barring we're going to be face-to-face again, but we're supposed to make those second semester, where you're going to mix two things together and it's going to get colder. That is evidence of a chemical reaction when you get warmer or colder. Making a precipitate is a solid product that is the result of a chemical reaction. It kind of looks like flour and water. It's a real fine powder that'll get into your liquid. So we will see a few precipitates as we go throughout the year as well. And then finally, if you're creating a gas or creating bubbles, that's evidence of a chemical reaction. The best example that I can give you of that is when you have your vinegar and you add it into water, or vinegar into baking soda, sorry. When you add those two together, you make water, you make carbon dioxide, which is your bubbles, and then you make another chemical compound, and that chemical compound is called sodium acetate. So, though it's actually endothermic as well, so that one will feel colder and it will make bubbles. If we think about lighting a match or catching something on fire, you have a color change, you have a new odor, you're creating light, you're creating heat, you're creating a gas, smoke. So there's many things happening whenever you are burning something. So it doesn't have to be one, it can be multiple. The law of conservation of mass says that mass cannot be created or destroyed. Nothing is ever created or destroyed. Energy is never created or destroyed. Mass is never created or destroyed. When you get into physics, momentum. So there's many different things that are never created or destroyed in chemistry. But we have the law of conservation of mass and the law of conservation of matter, law of conservation of energy. They're all identical. They all say that mass can never be created or destroyed, or matter or energy or whatever it is. It just transfers from one form to another. So if you look at the picture that's on the slide there, you have wood that's burning. Anytime something burns, it's burning in the presence of oxygen. If you don't have oxygen present, you're not going to have a combustion reaction. So you have wood burning with oxygen. With your wood burning with oxygen, your two products are always CO2, carbon dioxide, and water. And then you have your ash that's left over, which is a carbon-based compound. So as we go through that chemical reaction, you might say, well, the wood that I had weighed 20 pounds, and then now after it weighs a half a pound. I lost mass. That isn't actually the case. If you add the mass of the wood and the oxygen, you have the exact same mass of your product, which would be your ash, your carbon dioxide, and your water vapor. So if you start with 20 pounds, again I'm using non-metric, but 20 pounds of wood with your oxygen, you're going to make 20 pounds of product in the end with your oxygen, your ash, and your water vapor. So nothing is ever created or destroyed. It just transfers from one form to another. So when you think, hey, I lost a bunch of mass, typically that mass goes out into the environment, out into the atmosphere. So in the chemical reaction in the photo, you have a chemical reaction that's happening in an Erlenmeyer flask. That's that little triangular shaped flask. It has a rubber stopper on the top. So with that rubber stopper, it's holding in all of the gases inside of that chemical reaction. Right now, like the way that it's starting, you have a test tube that has one reactant in it. The flask has the other reactant. They're showing that you flip it upside down in order to get them to react together. The mass of the reactants in total equals the mass of the products in total. That is always the case. If you start with 500 grams, you're going to end with 500 grams. It just changes forms in some form or fashion. So with this math problem here, it says that we have 22.99 grams of hydrogen gas. It's reacting with 35.45 grams of oxygen. We want to know how much water will be formed. So what we're going to do here, in order to do the problem, we need to figure out how much mass we're starting with. So we're going to take our 22.99 plus 35.45, and that's equal to, let me see if I can do this. 58.44 grams. So if we have 58.44 grams to start, when those two react together, you're going to make, 58.44 grams for a product. The mass of the reactants is always equal to the mass of the products. Another question that they might ask you with this, with one of your problems that you're going to have to answer in the questions, it's going to say like, hey, you have 30 grams of a reactant and you know that you're making 50 grams of your product, but you don't know how much of the other reactant you are starting with. So it's like 30 plus X is equal to 50. So you're finding that missing component. So that missing component is 20 grams because you always have 50 grams on the reactants, 50 grams on the products, or 15 grams on the reactants and 15 grams on the products total. So you just go back to those like 6th grade math skills to figure those out. Now, with your pure substances versus your mixtures, we're going to take matter and we're going to break it down into some different components. I'm going to skip ahead a lot in the notes real quick, so bear with me just a second. And when we go ahead a lot in your notes, if I can find it, there it is. I have a flow chart here. And with this flow chart that I have here, part of it's kind of hidden. I apologize about that. But we're going to take matter, that overall concept at the top, and that matter that we have, we're going to break it up into 2 different categories. Your 2 different categories that it breaks up into is mixtures and pure substances. With the mixtures on one side, we're going to define the two different types of mixtures, and then pure substances breaks up into two categories as well, which is elements and then compounds is behind my little picture there. So matter overall breaks up into two categories, mixtures or pure substances. We're going to live over here in the pure substances for the majority of the year. At the very end of the year, like February or March, we're going to talk about mixtures in our solutions unit, but overall we're pretty much going to live in the pure substances. So we're going to take matter and we break it up into your two categories. The first category is pure substances. Pure substances cannot be broken down any further unless you go through a chemical change. So that means that you're completely changing the matter that's there. You can't boil it, or you can't, go through and do some sort of separating mixtures. You have to go through a chemical change to change what's physically there. There's two different types of pure substances. You have elements and you have pure compounds. Just compounds, sorry. Then you have your mixtures on the other side of that. Mixtures are two or more pure substances. So two elements, two compounds, an element in a compound, maybe two elements in a compound, something like that. And they can always be broken up by going through physical changes. So whether you're just taking your fingers and you're separating out, like if you have a bag of Skittles and you just want to eat the yellow Skittles, you can pick up the yellow and you can eat them. That's one way of separating a mixture, and then we'll have some more as we go through the notes here. So when we're looking at substances, usually you're going to find them in mixtures, which is kind of ironic because I just said that we're not going to talk about mixtures except for a little bit in the year. But most things in nature are found as a mixture. All mixtures, no matter what, all mixtures can be separated by going through a physical change. Those physical changes that we have, there are multiple kinds. We're not going to get into the details right now, that second semester. But maybe it's filtration. Like this little picture here, I've got a fish tank. In my classroom, I have a fish tank. The little fish go poop. That poop needs to get strained out of the water, otherwise they'd just be swimming in their poop, and that's not very healthy. So fish tanks have a filter. Mine's in the back of it. The water passes through and the filter catches the little fish poopies, and then the water keeps going through. So filtration is one type of separation technique. Chromatography, there's a picture. It has the little strips of paper here where you can take marker ink and you can separate it out based off of just separating it based off of their mass. So you can take the different substances and separate it that way. Distillation, we'll talk a lot about that second semester. Just by moving it, or physical separation, using a magnet, things like that are all ways that we can separate out different mixtures. Now there are two different types of mixtures. These should be a review from 6th grade and 8th grade science, probably before that as well. But you have homogeneous mixtures and you have heterogeneous mixtures. If you look at the root of those words, hetero means different. Homo means same. So if you have a homogeneous mixture, they're going to look the same all throughout. And then a heterogeneous mixture, or a heterogeneous mixture, depending on where you live in the country, you can see the different components that are there. So when you're looking at them, a homogeneous mixture, or some teachers say homogeneous, a homogeneous mixture looks the same all throughout. If you look at the air, you can't see the different components in the air, but air is a mixture. If you look at tap water, you cannot see the different components in your tap water. It's going to look all the same throughout. Heterogeneous mixtures, you can see the different components. So when I was talking about that bag of Skittles, with your bag of Skittles, you have your like grape Skittles and the red Skittles and the green Skittles, yellow Skittles, orange, I think that's all the colors, but you can see all the different parts that are there. Or a pepperoni pizza, you can see all the parts that are there. Are you hungry yet? So with all those different components, you can see them. So when you're looking at those words, hetero means different, you can see the different parts. Homo means same, so it's going to look the same all throughout. Okay, back to the pure substances. So we took our matter, we broke it up into two categories. We had mixtures on one side, the two different types of mixtures, homogeneous and heterogeneous. Now we're on pure substances, so we're back to the other side. A pure substance is a element or a compound. Elements are, let me turn on the lights real quick. There we go. Sorry. Your elements are pure substances cannot be broken down any smaller. It is the basic, most little thing of chemistry, basically. So you can have one atom of one element, but it cannot be broken down anymore. If you do break them down, you're going through nuclear reactions, which is something that we talk about second semester. So if you have zinc, which is an element on the periodic table, it's just zinc. You can't break it down anymore at all whatsoever because it's just the guts inside of it at that point. So some other examples, I just said zinc, but you also have gold and iron and oxygen and copper. All of those things are all examples of the elements. Elements are found on the periodic table of elements. So when you're looking at your periodic table, like if you have a test question and you cannot find it on the periodic table, it's not an element. Let's see, your elements, when you write them, it always has a capital letter first and then a lowercase letter. So, for example, if you have hydrogen, you would always write that as capital H. If you have phosphorus, phosphorus is capital P. If you have potassium, that's capital K. So when you're looking at your elements, it's always a capital letter first. You might have two letters. You never have more than that. If you have two letters in your element symbols, the first letter is always capital. The second letter is always a little letter or a lowercase letter. So what I mean by that is if you have manganese, manganese is capital M, lowercase n. If you have silver, that's capital A, lowercase g. So your first letter is always capitalized. The second letter is always a lowercase. Here I've got some more examples. I said hydrogen already, but helium is next door to hydrogen. It's number 2 on the periodic table. Helium is capital H, lowercase e. Iron is Fe. You're going to find out why those letters don't match in this class later on in the year when we get to the periodic table unit. But with your iron is Fe, capital F, lowercase e. Gold is Au. You're going to find out why that is. They don't match. It just doesn't match in English. But Au, capital A, lowercase u. Now with the periodic table that we have here, that is a way of lining out all the elements in a very organized manner. It has a very weird shape, but it actually all makes sense. We're going to dissect the periodic table a couple units from now. And we're going to look to see exactly why it has that shape that it does. And we're going to look at the different families and groups and periods on that periodic table. We're really going to break it down. But we're really just going to look at the chart overall, the periodic table, and we're going to look at just some key features because you're going to have to pull information off of that in order to get through the next few units before we get there. So when we're looking at these, we have your element name given, usually. So the element name for the element that's on the square here is called cobalt. So the name is cobalt. The symbol is CO. And as we found out before, not all of the symbols and the names match in English, but they actually match in another language, and we'll talk about that later. But the symbols are always capital and then lowercase. You also have the atomic number. The atomic number is the number that numbers it off on the periodic table. So that's the order on the periodic table. Hydrogen is number 1, helium is number 2, lithium is number 3, beryllium is number 4. So your atomic number is how it all gets lined out on the periodic table. And then you also have your atomic mass or atomic weight, depending on what we're looking at. Your atomic mass, we really just need 2 decimal places with this. So if I was writing this like on a worksheet or something, it would just be 58.93. The mass is the actual mass of one atom of one element of that in a unit called AMU, atomic mass units. So we know the mass of the elements themselves. Now the periodic table, we've just got a little bit left here, is arranged in rows and in columns. So the columns go up and down. Columns go up and down. Rows go across, which is horizontal versus vertical. Horizontal goes with the horizon, vertical goes up and down. With your rows and columns, they have special names. The horizontal rows are called periods. There's only 7 periods on the periodic table. Again, the periodic table kind of has a weird shape. When we number it off, like this red is period number 1, the orange is period 2, the yellow is period number 3, period 4 is the green one, 5 is this light blue, and then this like indigo purple color is all period 7. So what actually happens here is this is element number 50, I just lost it, 55, sorry, I usually know these. So element number 55 is here, number 56 is here, 57 jumps down to the bottom in this like weird row down here. And they basically just took out these 2 rows down here at the bottom to make the periodic table more condensed. Most of these are all radioactive. Most of these are man-made. We don't use them day to day. So that's where you're going to find neptunium and plutonium and americium and things like that. We don't really use these. So they took these 2 rows out here and they moved them to the bottom. So the purple actually all go together. So when you get down here to 103, 104 jumps back up here. I just said the wrong row. Sorry, those are pink. With your pink ones, again, you're going to number across. And as you number across, you're going to go like these 2 and then jump down here, go all the way across, and then back up to that row. So the periods, horizontal with the horizon. There's only 7. This is actually how the periodic table should look with those 2 rows out of there. So what I just showed you, 57 and 89 jumped down to the bottom, but we took those out and moved them to the bottom in order to see them a little bit better. Otherwise the squares are too small. Almost done, I promise. With your vertical columns go up and down. There's 18 of them. With your 18 of them, I'm going back a slide. This first column here is all group number 1. Second column is all group number 2. But then those 2 like weird little rows down here at the bottom, they don't actually have group numbers. So it's only the components up at the top. And so it goes group 1, 2, 3, and then down here to 12, and then 13, down here to 18 with helium. These are all called noble gases. But the 2 like kind of columns at the bottom, not columns, rows at the bottom, those do not have group numbers. So if I asked you what is the group number of samarium, it doesn't have one. So you would just leave that blank. Einsteinium doesn't have one. Thorium doesn't have one. But if I asked you about like scandium here, scandium is group number 3. Neon is group number 18. Lead down here is group number 14. So the ones at the top have group numbers. It's 1 through 18. Down here at the bottom, they don't have group numbers. The periodic table is called periodic because it does have a lot of patterns. It's how it's all arranged. So as we look at those different repeating patterns in the periodic table, it's an entire unit of all the different patterns, but periodic actually means in a repeating pattern. Most people say, oh, I do that periodically. Like, I don't know, I go to Target periodically. That actually doesn't make much sense. That would mean that you went every Monday. Or maybe you went every Monday, Wednesday, Friday. So you always went in a set pattern. So the way that people say that word and what it actually means are 2 different things. In the photo here, I have the periodical section of the library. The periodical section is where you're going to find your magazines and your newspapers because they're always released on the same day. I used to write for a magazine up in St. Louis when I was living there. And when I wrote for that magazine, my deadline was on the 20th of every month for my article. If my article was not in by the 20th of the month, I didn't get paid. But also, I didn't get published that month because it had to go to print after that so it could get released on the 1st of the month. So periodicals are always set on the same pattern. Now, a compound is two or more elements chemically combined together. So we have pure substances, elements are one type, compounds are the other. For your compounds chemically combining together, you can break them apart only by going through a chemical reaction. So if you have H2O, that's water, that's a chemical compound because you can write a formula for it. But you cannot break apart H2O unless you go through a chemical reaction. So maybe we electrocute the water. When we electrocute the water, we're making hydrogen and we're making oxygen gas. If you have table salt, NaCl, if you put it in water, that's just dissolving it. That's not going through a chemical reaction. Your table salt is still there. If you want to break that apart, you're going to have to find something to react with it in order to break it down into two different components. Oxygen gas is just O2. There's two oxygens there. Nitrogen gas, the major component of the air, is N2. There's more than one nitrogen or more than one oxygen there, so that's still considered to be a chemical reaction, or chemical compound. You should know how to read these as well, but you have your symbols and then numbers after it to tell you how many are there. So like H2O, H2 means there's two hydrogens. The O doesn't have a number after it. Chemists are lazy. We don't like to write the number 1 unless we have to. So their oxygen is there, so it's implied that there's 1. So with your letters and numbers, you're going to see symbols and then a number after it to tell you how many are there. You might also see parentheses. The parentheses actually is like the distributive property, where I have a 2 after my OH in parentheses here. With that 2 in the parentheses after it, that 2 actually goes to both of those, distributes to both of them, not the calcium, because the calcium is outside the parentheses. So here I have 1 calcium, because there's no number after my calcium. There's 2 OHs. So that means that I have 2 oxygens and 2 hydrogens. All elements start with a capital letter. So with that starting with a capital letter, I know that oxygen, O, is one element, and then I have another capital letter next to it, so that's your hydrogen. And I'll actually do this in a separate video, and that is pretty much all of your notes. So I just wanted to go back to this, and then I'll go back and I'll make the practice video on the dissecting different compounds. But when you're classifying your matter, matter is one topic in chemistry. It's anything that has mass and takes up space. There's 2 different types of matter, mixtures or pure substances. The 2 types of pure substances are either elements, which means they're found on the periodic table of elements, and then compounds, which are made up of 2 or more elements. And then your mixtures, those have 2 different components as well. You have your heterogeneous mixtures, which you can see the different parts that are there. And then you have your homogeneous mixtures. A homogeneous mixture looks the same all throughout. And that is actually the end of the notes, except for, like I said, I'm going to do one extra video with dissecting your different compounds. But at the end of each of the notes that you're going to see, you'll see a list, like that's given here, of all the different topics that you'll see on your test. So you'll be able to go to this and go, okay, I can do that, I can do that, I can do that. Oh, I don't know what accuracy and precision is, so then I would need to go back and review that. We'll also always do a review before your test. And I'll give you opportunities to ask questions as well. But you'll always have your topics to study, so that way you know exactly what you need to study for your tests for my class.